This video will introduce two of the most common prediction modeling methods, linear regression and logistic regression. As we have learned in this module already, models can be used to identify patterns and relationships between sets of predictors and a target dependent variable. Models are designed to automatically learn these patterns and relationships through a procedure known as model fitting or model training. Different model structures are able to learn different types of relationships within data. Linear models, such as linear regression and logistic regression, can learn linear relationships in data. To illustrate this, let's consider an example case where we want to predict test scores using study time as a predictor. We can go out and collect some data consisting of the time that students devoted to studying and also the score that they received on the associated test. If we were to plot that data, it might look something like this. From this example, we can see that generally speaking, students who spend less time studying receive lower test scores. And as study time increases, we see a positive trend with those scores. If we find a line that best fits our data, we might get something like this. We see that the line doesn't perfectly fit our data on every point. There's some variance where some points are further off the line than others, but it captures the general trend. Effectively, this is what linear regression modeling accomplishes. It simply finds the single line that best fits our data. That is, it finds the line that minimizes the amount of error as measured by the distance of each sample to that line. As a prediction model, once we learn this line, we can use the linear regression model to predict the test outcome of new samples, so long as we know how much time that the student spent studying. If we have a student that spends this much time, for example, as indicated by this green line, our best prediction for their score would be where this green line crosses the line of best fit. Functionally, we can express this linear model as a linear equation. If you remember the equation of a line, often expressed as y equals mx plus b, we can redefine these terms such that y is our test score, our dependent variable, x is our set of predictors. We might have more than one, but in this case, this would be our study time. B is our bias term, or our intercept. And we effectively want to learn what the slope of that line is, represented by a coefficient. So we supply the model with a set of example cases of x's and y's, of our predictors and our labels, or our dependent variables, and it attempts to learn the coefficient. It learns what m, or beta, as the Greek letter that's commonly used, it tries to learn what that value is, as well as what the intercept is. The coefficient, representing the slope of the line, quantifies the relationship between our predictors and the dependent variable. If we learn that this value is 0.4, for example, it suggests that for every 1 unit increase of time, we tend to see 0.4 more points on the test. Remember, however, that unless we pair this model with other experimental designs that allow for us to make causal claims, we are limited to correlational conclusions. In other words, this doesn't necessarily suggest that we can just improve test scores by forcing students to spend more time studying. Linear regression fits a line to the data, which is best applied when we have continuous valued dependent variables, something like a test score. But when we have binary data, a logistic regression model is typically more appropriate. Logistic regression will find the best line that separates the two classes within our binary data. Let's say that we don't have continuous valued test scores, but instead simply have high and low value indicators. Perhaps this is a pass and fail grade, to give a concrete example. If we plot the same data as we had before, it might now look something like this. Logistic regression wants to draw a line that best separates our classes by fitting a slightly different function to our data. To be more precise, the model is actually fitting a logit function, which follows this type of S shape, but the concept remains the same. We are trying to find the line that best discriminates our two classes of high and low test scores. What the model produces is a value between 0 and 1 that represents the likelihood of the positive class. That is, it can be interpreted as the probability of a student receiving a high test score, in this case. In mathematical form, we can see that the logistic regression model looks very similar to a linear regression with just the addition of this logit function. It is important to remember that both linear regression and logistic regression are linear models. They can only model linear relationships between predictors and dependent variables. That means that if the actual data were to look like this, where we see some amount of diminishing returns as study time increases, a linear regression model would be unable to fully represent this relationship. Instead, it would still minimize error to find the line that best fits the data. This is a concept known as underfitting, where the model doesn't have the necessary complexity to capture the relationships in the data. This is contrast to a related concept known as overfitting, where the model is overly complex, but we'll visit this concept a little bit later. Other assumptions made by linear and logistic regression are that the predictors are independent. If you include variables that are highly correlated with each other as predictors, the model may not be able to converge effectively. This is an issue known as multicollinearity. There are variants of linear regression, known as lasso and ridge regression, which help to account for collinear features. Without these methods, however, it's typically a good idea to examine the correlations among your predictors and remove those that are found to be highly correlated with others.